Imagine you're a chemist trying to forge a bond between carbon and fluorine. It sounds simple enough, but in the world of organic synthesis, fluorine is a notoriously difficult element to handle. It's the most electronegative atom on the periodic table, a tiny, aggressive electronics hoarder that often reacts so violently it tears molecules apart. So, how do we introduce fluorine into an organic chain without causing a miniature explosion? For that, we turn to a classic transformation known as the Swartz reaction. Let's look at the basic setup. Typically, we start with an alkyl chloride or an alkyl bromide, molecules where carbon is already bonded to a halogen like chlorine. Our goal is to swap that chlorine for a fluorine. But if you just toss in a simple salt like sodium fluoride, almost nothing happens. The bond we're trying to break is stubborn, and the fluorine ions aren't quite pushy enough to force the swap. This is where the magic of the Swartz reagent comes in. Notice this compound appearing on screen, antimony trifluoride, or antimony 3-fluoride. By itself, it's a decent fluorinating agent, but the real secret lies in adding a tiny bit of antimony pentachloride as a catalyst. As you can see in this molecular dance, the catalyst reacts with the antimony trifluoride to create a much more potent mixed metal cation. This activated complex is the key. It doesn't just ask the chlorine to leave, it practically pulls it off the carbon chain. Let's visualize the mechanism step by step. Picture our alkyl chloride. The carbon-chlorine bond is polarized, with the chlorine pulling electron density toward itself. Now, watch what happens when the antimony metal approaches. The antimony has a high affinity for chlorine. It wants to snatch it. As the antimony interacts with the chlorine atom, it weakens the carbon-chlorine bond to the breaking point. And here's the key insight. As that old bond stretches and breaks, a fluorine atom from the antimony complex is perfectly positioned to take its place. It's a coordinated swap. Think of it like a meticulous trade. One halogen leaves while the other is escorted in, preventing the molecule from falling into a chaotic state. But wait, why do we use antimony instead of cheaper metals? Well, look at the thermodynamics. The reaction is driven by the formation of a much more stable antimony chloride bond. We are essentially trading a carbon-chlorine bond for a stronger, more stable carbon-fluorine bond, using the metal as the heavy-lifting intermediary. This reaction is particularly famous for creating freons, or chlorofluorocarbons. While we now know the environmental challenges these molecules pose, the Swartz reaction remains a foundational pillar of industrial chemistry. It taught us that when an element is too reactive to handle directly, we can use a metal handshake to get the job done. So, the next time you see a fluorine atom perfectly placed in a complex medicine or a high-tech polymer, remember the Swartz reaction. It's a reminder that in chemistry, as in life, sometimes the most difficult changes require the right mediator to find the path of least resistance.